this opportunity. I'm Patrick presenting on behalf of my co-authors as well. And I'm presenting on the topic tomato disease fusion and the classification using deep learning. My co-authors are Sumit from KIT. We also have Professor Ezhil from University of West Florida, as well as Caroline Johnson.
You need some to cover your head. Like a scarf. Yeah.
Also from, thank you very much. Also from West Florida University. I'll go quickly to the introduction. It came to our notice that tomato being a very important crop, which is being produced worldwide, it's actually of that is facing so much issues when it comes to disease attacks. And then in general, we found out that about 30% of crop loss is being contributed by crop diseases. And one thing which actually drew our attention to the fact is that most of these diseases usually affect the leaves. Now, the leaves of plants, as we know scientifically, contribute a lot to, or is actually the main backbone of photosynthesis, which is the growth, which contributes to the growth of the plant. And we realized that there were a variety of various symptoms and pathogens which were actually behind these diseases. Now, here we looked at tomato disease, and we decided to also go into a more complicated form. But before we go to the complicated, or we look at the complicated nature of it, we would want to look at the various diseases which we considered in this particular section of our research. We had some likes of late blight, leaf mold, septorial leaf, which we have in the middle here, spider mite, and then the bacterial spot. These were just a few of the diseases which we looked at. We decided to employ image processing, which is actually a manipulation skill and a way of also extracting visual data from images. And we introduce a new methodology, which actually brings into consideration creating more complex or complicated nature in analyzing or in getting much more information when it comes to diseases. Now, there are these situations whereby farmers were using their eyes to actually try to detect certain diseases. And we saw it to be a problem, and therefore to have impact or to make impact on our society after our studies in school, we decided to employ machine learning or artificial intelligence, specifically in deep learning, to do this. So we thought about, what if there be a situation whereby a plant may be having much more than, or a tomato plant may be having much more than a disease on the plant? So we decided to actually move away from the normal workflow whereby scientists or researchers actually use one disease on a leaf situation, as we've been doing in most situations. And therefore, we decided to actually complicate the issue, and therefore looking at a more complex neural network, or we build a more complex neural network using a very strong back-end situation to actually also learn very complex structures which will be formed in the process when learning. So that actually encouraged us to go ahead and then also do this particular experiment. We therefore employ deep learning to also learn the traits which overlap in the various disease traits, which would also, or which I would also explain further in the preceding pages. So I'll quickly go to the proposed methodology. So here we have our data collection, which we collected from Kaggle. As we can see from our chart here, we took it from Kaggle, which contains 16,024 images with 10 classes. And then we proceed to data pre-processing, where we looked at normalization of the process or of the data or the images by resizing all data size, which was actually 255 by 255 pixel. What we did to the normalization was to actually write a code within the model to downsample it between 0 and then 1, and therefore creating a more normalized data for us. We proceeded to data splitting and fusion, which is the backbone of our research. And what we did was that we were able to merge, or we splitted various disease plants or seeds, various disease leaves rather, of various classes, and then we merged them, hence creating a more complicated nature. Therefore, on a particular leaf, we could be having two or more different diseases as thought before, which actually led to this particular situation which we looked at. So from there, we therefore went on to create a model using Keras TensorFlow as back end. Now we employed Keras or TensorFlow because Keras happens to be an open source deep learning framework written in Python. Now we also found out that it was developed by Franco Charlotte, and then it became part of TensorFlow in 2017. And this actually helped to solidify its absorption into TensorFlow, which is the Keras absorption into TensorFlow, helped to solidify the position of TensorFlow as a higher level neural network API. Keras provides a simplified interface for constructing, training, and then deploying of deep learning models. And it also supports both convolutional and a recurrent neural network. We therefore went on to train and then test our model for performance evaluation. And finally, we will get to our results. So we look at the backbone of our research here, which is basically the splitting and then the fusion, which we did to actually see how much complicated our system would be like to also help us to find as many as possible diseases on a particular leaf. Now, in this situation, since this is the beginning of our research, what we did was that we only splitted two different classes and then merged the different halves. So for instance, we could go to the likes of, so we have two merged disease leaves here. If we look at this image, which we have here, we have the healthy tomato leaf being fused with a leaf mold, which happens to be a disease. So this actually creates a situation whereby, assuming we have a particular tomato leaf, now it could be that half of the leaf or a part of the leaf may be healthy, and then a part of it may be having what the mold disease. Here we also have here the septorial leaf disease and then the late blight disease. So there could be a possibility whereby a leaf is carrying two diseases as we have here, which in the future we may be looking for more or less more than two diseases on a particular leaf, because we wouldn't want a situation whereby a farmer is advised that this particular disease or one particular disease is on a plant, but he or she administers the necessary preventive skill or necessary medication, and then later he finds out that there is also another kind of disease. So we're thinking about a situation whereby we could identify as many as possible diseases on a particular leaf or of a plant, or specifically of tomatoes, so that it could actually be dealt with completely, or let's say on an outright situation. So from the 10 classes which we had previously, what we did was that we splitted them into we splitted each image within each class, and then we fused them with different classes. And we came out with 20, we decided to work with 20 new subclasses. And then we decided that each class should have at least 750 image in each class. And therefore, with 20, we would have 15,000 images for our training process, or that is a training and learning process, or for our research work. That's what we actually did. Now, I earlier said that we employed the Keras TensorFlow, which I've explained. And then what we did was that in Keras, or in TensorFlow, there are two ways of actually constructing our model, because here we went to the classification model creation. What we did was that, first and foremost, what we did was that we actually splitted the data into three halves: 80% for training, 10% for testing, and then the other 10 for validation. We employed a sequential API instead of the functional API, because in the sequential, it actually helps us to form, or it's actually a linear stack of layers where layers are added one at a time, so that it could help us to also modernize, or let's say modify our model as we go on in the training or in the learning stage. So it also expected a batch size, and we gave it a batch size. So we took a batch size of 32 for our kind of data we had, and then we maintain an image size of 255 by 255 with 3 channels because of RBG. And then what we did was that we trained these models 3 times using epochs of 4 for the first training. We did another training or a learning process, which we did 10 epochs, and then the last one, 50 epochs. So Within our convolutional neural network, which we created on the sequential API, this is what we did. Our initial convolutional layer had 32 filters with 3 by 3 kernel, a ReLU activation, and then a 2 by 2 max pooling. This is basically the kernel here, or if we look at the filters, filters are small matrices which help to extract features from input data. They also provide a local representative, that is to determine the size of the input data coming in. They actually have shared parameters. And then also the kernel, which also works more or less like the filters, also extract features from input data. Now, the ReLU introduces a nonlinearity function into the system by creating it in such a way that any other feature which was escaped during the early processes are actually observed and then extracted by this activation function. And then we ended this first layer using the max pooling. The max pooling, the function of the max pooling is to downsample the spatial dimension of the features, because actually the result of a convolutional neural operation is a feature map. So to downsample the feature map, we introduce the max pooling to downsample it so that we could move on to the next stage or the next layer. The next layer, which happens to be the intermediate convolutional layer, we actually use two intermediate convolutional layers here: a 64 filter, and then a 3 by 3 kernel, followed by a ReLU activation function, and then a max pooling function, which happens to be a matrix on its own. And then we also went on to introduce the fourth layer, which happens to be the flattening and then the dense layer. Now, the flattening helps to flatten the resultant features of the resultant featured map, into a one-dimension vector, because we're heading towards the end of it, which is the output side of it. And then we also introduce a non-linearity or activation function, which happens to be the ReLU, which we use there. We also use the dense layer because the dense helps to learn complex features, that is higher level patterns and representations within the neural learning process. And then finally, we introduce the output layer, which is a dense layer made up of a dense layer to continue to learn complex structures, and then a softmax function. The softmax permits the model to yield to class probabilities as output. That is, it's to help us to produce the final output or prediction of a neural network. Without that, we won't be able to predict what kind of validation or accuracy we have within our training stage. So we introduce the softmax in there. We quickly move on to the evaluation of the output parameters. Now, in here, in the first particular epoch we ran, which was a 4, we actually obtained an accuracy of 0.93, which is equivalent to 93%, with precision of 9%, which is 0.9, 0.5 for recall, and an F1 score of 0.7. The F1 score happens to be the harmonic mean of the precision and then the recall. Now we clearly see that accuracy was high, precision was low, and then recall was equally low. Now we're looking at how complex the system is, in the sense that it's actually this neural network is trying its best to learn from a more complicated situation. Because here lies the case, it is not having a uniform, just one leaf uniform system, but it's actually having different kind of structures which are being put together. Because if you remember in the first stage, we talked about overlapping traits. So here lies the case, we had overlapping traits which our model was supposed to, as precisely as possible, learn and recall from. And it was very difficult for it. So looking at 4 epochs, we had very less precision. We therefore went on to increase the epochs to about 10. And in that situation, we maintained, or it actually maintained, an accuracy of still 93. That tells us that at that particular, between these intervals of 4 and 10 epochs, the learning process had gotten to its limit, and it would only give us a particular accuracy which is of the same amount. But precision and recall got elevated a little bit, and therefore affecting the F1 score. The F1 score helps us, or helps to actually differentiate between the false positive and then the false negative. The false positive and then the false negative actually are the error functions, because the false positive has to do with the type 1 error, and then the false negative also is a type 2 error. So to actually work accurately, or for a model to actually work accurately, we need a higher F1 score, meaning that it's able to correctly move around these situations of making errors, and rather creating a very good situation of predicting well. Hence, if an F1 score is high, we expect precision and recall to also be high. But if it is low, precision and recall automatically will be low. So we see its effect in the situation whereby we have 50 epochs. 50 epochs give us an accuracy of 95%, which is 0.95. And we could see that when the learning process or the training stage is actually increased, which is the number of epochs being increased, it affects accuracy, precision, recall, and then the F1 score as well in general. And we can clearly see it in its prediction. So we look at the learning and then the loss curve for 10 and then 4 epochs. We can clearly see that in the 4 epochs, which happens to be this particular one here, we actually don't see a kind of covariance which is happening between both learning stage, especially in the training and then the validation accuracy. We just see them acting as, let's say, straight lines, almost or more or less like straight lines moving in its own way. And this clearly shows its impact on the precision and recall, very less, as we see there. 10 actually showed a level of covariance around this area, which is a level of more or less like a good learning situation, because we're looking at the learning curve and then the loss curve in here, and we can clearly see an upgrade of it. If we also go on to look at the learning and then the loss curve for the 50 epoch, we see how learning went on in the training and validation accuracy. The learning curve was so well structured, and hence, if we look at these, or if we compare these particular learning stages and training stages, looking at the learning and then the loss curves of the various epochs which were run on the same model, we realize that we will surely have much accuracy in prediction when it comes to considering the 50 epoch model. We quickly move on to the validation, the other stage of the validation, where we're going to do prediction. We tested our our model, which is the 4 epochs model, on the test data set, and then we provided it with the first and foremost, we provided it with an image which was made up of tomato leaf blight and then target spot. We found out that it predicted the test data set which was provided to it as leaf mold and bacterial spot with a confidence of 24.11%. This actually depicts what it came out with as its parameters for precision and then recall as low as possible, therefore affecting the F1 score. They were very less. Hence, we were not actually surprised seeing these kind of predictions being made by the 4 epochs. The same went on when we gave it another data set as well, which was tomato spotted spider and then a mite tomato healthy leaf. We gave it this particular kind of thing for it to look at in order to predict, and then it did otherwise by predicting a different kind of a different kind of disease, which was not actually in line with what we gave to it. So we saw that the 4 epoch model wasn't actually accurate as seen or by its output parameters, which is recall and then precision. Now, we therefore also went on to test our 10 epochs model. It actually gave us one correct prediction and then also one incorrect prediction, hence creating an inaccurate situation versus an accurate situation. Now, let's look at the accurate situation. We provided with a mosaic tomato early blight disease, which is a joint disease, and then it's predicted correctly with an accuracy or confidence of 80.82%. That shows that the 10 epoch model was learning better as compared to the 4 one, or as compared to the 4 epoch model. And then when it's actually downsampled and then predicted wrongly, it gave a confidence of 20.88, which is very less. Hence, when the confidence of its prediction is very less, we are possible or we will possibly see a wrong prediction, as seen here, because the actual data set was mosaic virus fused with tomato early blight, but it predicted leaf mold fused with healthy, which was not true. And therefore, its confidence even staggered at 20.88%. That shows how, when it's actually going to predict wrongly, it was going to actually do this. Now, we're not shocked with all these parameters because this was actually a very test situation for us, which we were on a road, or we are on the road of actually coming out with a more substantial, robust model that can actually predict two or more diseases more accurately using a very robust situation. So all these things helped us a lot in our learning process. We also go on to look at the 50 epoch, how accurate the prediction is, and then how high the confidence is. In the first place, when we look at the 50 epoch, it actually gave us a true positive of 37 um, um, badges in here. And then, 37 for true positive, false positive 34, false negative to be 37, and then true negative is 1,391 with a validation loss of 1.099 and then a validation accuracy of 0.625. We'll look at its impact in prediction situation. With its impact, we clearly see that, okay, I was checking if I was online. I'm sorry for a short break. Internet here, an issue, so I was just checking if I was online. Now, its prediction impact, we clearly see that it actually predicted at a confidence of 99.82%, whereby it predicted rightly a leaf blight tomato leaf, which was fused with a target spot disease. And that was very wonderful because we clearly see an impact growth when it comes to the increase of epochs in the learning situation. Now, we look at an incorrect prediction whereby it gave a confidence of 82.12%, it predicted wrongly. This gives us a four insights that we need to actually work on, or do our model work correctly sometimes, and sometimes it also doesn't work correctly because we had two situations whereby it predicted incorrectly. We had tomato leaf prediction with early blight for a case where it was provided with septorial leaf spots and then yellow kale. This wasn't good for us, and we actually accepted it because we're looking at a more complex or a complicated situation, which we would be looking at in the future process. So in conclusion, we accept and we actually believe that we have proven structural complexity by splitting and fusing of different leaf affected with diseases to create complex disease pairs. And then also improved, or we actually looked at the improvement of our prediction by increasing the learning processes, which is the learning, the number of epochs which we use in training. And also, we also suggest and we predict that the splitting and fusion method is going to be a candidate methodology for predicting multiple diseases on a single leaf. So for future work, we look at actually advancing this by building a more robust model capable of predicting multiple diseases more accurately and providing a level of severities of the diseases even from its early stages as well. So I bring my presentation to an end and I open up for questions. Thank you very much.